This talk deals with some neurophysiology topics. This is the second section in a 4-part series. These are the session outcome. You do not need to read them. They will be covered during this session. This talk will be conducted in a question and answer format. The first question is, which of the following statements is not true regarding ionic and capacitance currents? A. Both currents can contribute to the production of an action potential. B. Both currents result from displacement of charges. C. Both currents involve channels. Understanding ionic and capacitance current is paramount to understanding action potential propagation. I will first talk about ionic current. In this frame, I have represented a patch of cell membrane. The green structure represents a gated sodium or calcium channel with a closed gate. The membrane potential is -70. The circle with the plus sign represents a cation, sodium or calcium. I have now represented just below the same figure but with the gate open, and now represented the cation going into the cell and making the inner membrane surface less negative, from -70 to -40. This is an example of ionic current. Hence, ionic current can be defined as the current generated by the passage of charges, in this case positive charges through channels embedded in a membrane. Now we are going to talk about capacitance current. The concept of capacitance current is less intuitive. This is the same figure I showed you before, so I will not point out the different elements. The figure below is the same as the figure above, but unlike the one in the frame explaining ionic current, in this figure the gate of the channels is closed. In capacitance current, the rise in membrane potential is due to 3 factors. 1. The arrival of intracellular cations. 2. Their desire to leave the intracellular confinement. 2. Their desire to leave the intracellular confinement, as indicated here. And 3. The repulsion of the positive charges on the outer surface of the membrane, as indicated in this frame. This process makes the inner membrane surface less negative, let's say from -70 to -40. Hence, capacitance current can be defined as the current generated by the arrival of positive charges to the inner membrane surface and the displacement of positive charges from the outer membrane surface. So the answer to this question is C. Next question. The intracellular flow of positive charges from one segment to the next is called A. Action potential, B. Ionic current, C. Capacitance current, D. Electrotonic conduction. Understanding electrotonic current is of paramount importance to understanding action potential propagation. This is a cartoonish representation of a neuron. Here I have idealized 2 dendrites and an axon as cylinders and the cell body as a sphere. Electrotonic conduction or current is the term used to denote the flow of positive charges from one segment of a neuron to the next. That is, from one segment of a neurite to the next, from dendrites to cell bodies, and from one section of the body to another. Electrotonic current, although represented here as dissipating in only one direction, it does so in all directions. I am now indicating to an axon segment. We will use the axon segment to illustrate electrotonic conduction. Electrotonic conduction can be visualized as the flow of positive charges through intraaxonal compartments as represented here. So the answer to this question is D. Next question. The effect of electrotonic conduction through neurites and muscle fibers can be compared to walking. A true, B false. The effects of electrotonic conduction in fundamentally cylindrical structure like neurites and muscle fibers can be compared to walking. A person taking long strides walks faster than a person taking short strides if the time taken for the strides is the same by both persons. Neurites and muscle fibers conduct electricity faster if the distance from the place of initiation of the depolarizing current to the place where the current is no longer able to depolarize the membrane is longer than if it is shorter. The term length constant is used to measure this element of conduction. Thus, for the purpose of nerve conduction, length constant, also called space constant, can be defined as the distance electricity travels within a neurite before voltage drops to 37% of its original value. The longer electricity travels before dropping to 37% of its original value, the longer the length constant. The longer the length constant, the further along the depolarizing force will travel in the neurite. Thus, the faster the conduction. So the answer to this question is true. Next question. The factors that influence length or space constant are membrane resistance and axial resistance. A true, B false. Now we will go back to the axon to explain the factors involved in length constant. As previously mentioned, length constant refers to the distance electricity travels within a neurite before the voltage drops to 37% of its original value. Length constant is influenced by membrane resistance and axial resistance. It can be calculated by finding the square root of the division of membrane resistance by axial resistance. I will explain this in the next few frames. Let's look at the figure of an axon segment. Membrane resistance can be viewed as holes in the membrane cylinder through which positive charges can exit. Membrane resistance will be low if there are many holes. Membrane resistance will be high if the number of holes are very few. We will represent membrane resistance by the electrical symbol of resistance across the membrane. Axial resistance can be thought of as the diameter of a cylinder. Either making it narrower will increase axial resistance or wider will decrease axial resistance. As shown here, axial resistance will be represented by the electrical symbol of resistance through the cylinder. So decrease axial resistance and increase membrane resistance increases length constant, thus extending the depolarization zone further along the axon, whereas increasing axial resistance and decreasing membrane resistance decreases length constant, thus decreasing the speed of conduction. So the answer to this question is A. Next question. Increasing membrane resistance increases length constant. A true, B false. In this frame, you can see in the y-axis voltage, in the x-axis distance in millimeters. The dashed line represents a 37 drop in voltage from the onset. The voltage onset is represented by the magenta plus sign. I have now introduced the factors involved in length constant and a cartoon representing an axon segment with increased membrane resistance and decreased axial resistance. In this frame, you can see the effect of low axial resistance and high membrane resistance on length constant, as represented by the green line. I will now introduce the opposite situation. You can see an axon segment with decreased membrane resistance and increased axial resistance. I have now represented the corresponding voltage drop in relation to distance travel by electrotonic current in a neurite. As you can see, the axonal segment with increased membrane resistance has an increased length constant. So the answer to this question is true. Next question. Time constant can be ignored when considering electrotonic conduction. A true, B false. An ideal axon will have an infinite high length constant and an infinite low time constant. Thus, an action potential in the initial segment would instantly produce a synaptic neurotransmitter release. There's not such a thing. We have already talked about length constant. I will now address time constant. The time constant refers to the time it takes electricity to charge a membrane to 63% of its original value. Time constant is directly proportional to the resting membrane potential, which I will represent in this axon segment by the electrical symbol for resistance through the membrane as we did in the past, and membrane capacitance, which I will represent by the electrical symbol of capacitance across the membrane. Can time constant be ignored as a factor in electrotonic conduction? The answer is yes. Why? In this frame you can see represented an axon with long myelinated segments. Action potentials only occurred at two places. Hence, conduction slowing only occurs at two places because electrotonic conduction is instantaneous, as represented in this frame. Electrotonic conduction advances current without consuming time. The extent of the advancement is a function of the length constant of the neurite, in this case of the axon. But unlike the action potential indicated here by the two arrows, it is not influenced by time, at least as best as we can measure time at the moment. So the answer to this question is true. Next question. Increasing length constant increases axonal conduction. A true, B false. Action potentials decrease the speed of conduction because even in the case of simultaneous arrival of a depolarizing current to a membrane patch, charging the membrane to trigger the action potential takes time, and because the action potential itself takes time. Electrotonic conduction advances without effectively charging the membrane nor producing action potentials. Hence, it does not take time, at least not the way we measure time at the moment. In the following frames, I will give some examples that illustrate these points. In unmyelinated axons, conduction advances by the production of action potentials in subsequent axonal segments, as represented here. Time constant by determining how long the patch of membrane takes to charge prior to the production of an action potential is one of the deciding factors on the speed of conduction. Notice the length of the arrow representing time. In an axon with short segments of myelination as represented here by the yellow rectangles, action potential occurred at relatively close intervals. Electrotonic current carries the depolarizing current from one action potential to the other. Electrotonic current decreases the need for action potential to advance current, thus increasing conduction speed because electrotonic conduction travels instantaneously in the segment of axon covered by myelin. Hence, length constant becomes an important factor in myelinated axons. Notice the length of the arrow representing time. In this frame, you can see represented an axon with long myelinated segments. Action potentials only occurred in two places. Hence, conduction slowing only occurs at two places. Now I have represented electrotonic conduction. Yet, electrotonic conduction advances more because the myelinated segments are longer. In this representation of an axon with long segments compared to the representation of the axon with short segments. Therefore, conduction through axons with long myelinated segments is faster. Notice the length of the arrow representing time in this frame. In this frame, I have put together the three examples you just seen. The longer the intraaxonal current travels by electrotonic mode, the faster conduction takes place. So the answer to this question is A. Next question. Myelin increases membrane resistance by decreasing the number of channels in the internodal region. A true, B false. This is a cartoonish representation of the distribution of sodium and potassium channels in an unmyelinated axon. Notice that the channels are evenly distributed throughout the axon. This is a cartoonish representation of a myelinated axon. Notice that channels are congregated in the nodal and perinodal region. The increase in membrane resistance as a consequence of reduction in number of channels increases length constant. The increase in length constant by increasing the intraaxonal distance traveled by the depolarizing electrotonic current decreases the frequency with which the membrane needs to be charged and the need for action potentials to be triggered. So the answer to this question is A. Next question. Myelin increases length constant by decreasing membrane capacitance. A true, B false. Cells membrane have a capacitance of 1 microfarad per square centimeter. In this frame, I am representing a segment of a cell membrane and a row of negative charges outside the cell abutting the cell membrane. As you know, negative charges exert a strong attractive force upon positive charges across a membrane. This force is influenced by distance, a very important point to keep in mind during the process of answering this question. The further the charges, the lesser the force. So if we imagine a gun capable of shooting positive charges and this gun fires 4 positive charges, these positive charges will feel a strong attraction exerted by the negative charges since the distance between them and the negative charges is short, as you can see in this figure. As a consequence, the progression of positive charges along the membrane will be limited, as you can see. At this point, the attraction would prevent further progression of positive charges. So let's say that positive charges advance for 1 centimeter. Now let's see what would happen if the cell membrane is thinly myelinated. Let's say that now the capacitance is 1/3 of what it was when unmyelinated. As represented in this drawing, the yellow rectangle representing myelin, again we have the gun that fires positive charges, but since now the negative charges are further, they exert less attraction upon the positive charges, thus they travel further, as you can see reflected here and here. So as you can see, it has taken the attractive combined forces exerted by 2 negative charges to attract a positive charge. Hence, the positive charges advance further than they did in the membrane with no myelin, let's say 2 centimeters. Now let's look at a membrane covered by thick myelin, leading to the drop in attractive forces to 1/5 what the unmyelinated fiber had. This is represented here. Again, the gun shoots 4 positive charges. The positive charges feel the weak attractive force exerted by the negative charges that are now further than they were before, so the positive charges will advance more, as you can see here. It has now taken the combined force of 3 negative charges to attract 1 positive charge. So now the positive charges have advanced 2.5 centimeters, half a centimeter more than in the last example. In this figure, I have summarized the effect of decreasing capacitance by increasing the size of the myelin around the axons, which I will label A. I have done so to compare with another factor that I will label B. This factor is the effect of myelin of driving voltage-gated channels away from the internodal region. This later effect, that has the consequence of increasing membrane resistance, has a stronger effect on increasing the length constant than the drop in capacitance. So the answer to this question is true. Next question. Ohm's equation states all of the following except. Please take a look at the different options and choose the one that is incorrect. The easiest way for me to remember Ohm's law is thinking of this triangle with the lines inside as drawn here. This line indicates division and this line indicates multiplication. Then I place an E on top to indicate electromotive force. Electromotive force is measured in volts. Below, I place letter I for current. Current is measured in amps. Next, I place the letter R. The R is for resistance. Resistance is measured in ohms. Once the triangle is filled, I put my thumb to work. I do so by covering the letter before the equal sign in the triangle. If the expression after the equal sign matches the operation suggested in the triangle, the equation is correct. Now let's look at another example. To work this equation, we cover the letter I because it is before the equal sign. As you can see, the expression after the equal sign matches the operation suggested in the triangle. And now let's look at the last example. Using this equation, I will again use the thumb to cover the term prior to the equal sign, in this case the R, and as you can see, the expression after the equal sign matches the operation in the triangle. So the answer to this question is D. Next question. The higher the resistance, the stronger the electromotive force created by a given current. A true, B false. In this frame you can see 2 ohms triangles. I have now introduced a current in both triangles with a value of 3 amps. Now I have introduced the resistance in the first triangle with a value of 4 ohms. These numbers will generate an electromotive force of 12 volts. I will now go to the resistance in the second triangle and introduce a value of 6 ohms. That is 2 ohms more than in the first triangle. These numbers will produce an electromotive force of 18 volts. Hence, the higher the resistance, the stronger the electromotive force created by a given current. So the answer to this question is true. Thank you very much for your attention.